Okay, so in this video, we're going to take a look at non-equilibrium in rotation, and I'm just going to do this using a case study, a particular example, and I'm going to do it in such a way that I actually end up using two different perspectives to answer the question, because I think it's important that you see how you can have options available to you, different pathways which lead you to whatever answer it is that you're looking for. So what we're attempting to accomplish with this particular case study is just find out how fast will this block be moving whenever it falls through some distance of d. That's all we're interested here in this particular problem. Now, what we have is less than an ideal case because we have a pulley which is heavy and the block is hanging from it, so the pulley is going to interfere with the block. Obviously, the block does not accelerate at 9.8 meters per second squared, so how do we deal with this? Well, we're now studying perspective number 2, which is forces in rotation. And in AP Physics C, forces tend to be a bit more sophisticated. So we had non-equilibrium last year, and very often in those non-equilibrium cases, you just had to find an acceleration for a disk which maybe was spinning up to a maximum speed, or slowly it came to rest on its own. Just other variations on a relatively straightforward problem. But in AP Physics C, of course, they like to make things a bit more involved. And so what we have is, in this case, we have translational motion being combined with rotational motion. So of course the translation is going to be for our block, which is going straight down, and then the rotation has to do with the pulley. And of course the one thing that puts the two together into one is the fact that we have our bridge equations. Because the string is unwrapping from the edge of the pulley, we know that the speed of the string, which is also the same thing as the speed of the block, is going to be the same speed as the tangential edge of the pulley. So let's go ahead and get started with this. We set it up like we do any other force problem, and that's going to start with Newton's second law. So we have tau net equals I alpha. And from here, we need to define what tau net is. So before we can do that, we have to draw our FBD for the pulley and the block. Okay, so when we look at the forces acting on the pulley, we have the force of gravity, which is acting through the center of mass. We have the force of tension, which is pulling straight down on the edge of the pulley. And then we have a normal force which is pointing up, which is not necessarily equal and opposite to the force of gravity which is pulling down on it, because we have interaction between both the block and the pulley. So the weight is part of it, and then the weight of our block is also going to be part of it. Okay, so we really don't precisely know what the normal force is going to be. We can figure it out, but you cannot just assume that the normal force is equal to both the weight of the pulley plus the weight of the block. And then finally, we draw our forces on our block, and we have a tension force which points up, and then the force of gravity from the block pointing down. Okay, so this was the normal force. This is the force of gravity of the pulley, or the weight of the pulley. This is going to be the tension force here. This is the same tension force. It's the same length of string, and therefore it's going to be the same in magnitude because the tension is everywhere the same in a string. And then finally we have the weight, or the force of gravity, for the block. In terms of forces that are going to cause torques, because that's what tau net is all about, torque. In order to answer that question, we have to figure out what our axis of rotation is going to be. Now, the obvious axis of rotation is going to be in the center of the pulley, or the axle of our pulley. So that's going to be our axis of rotation there. Okay, so we know that we've got three forces acting on our pulley, so technically we could write those in. So we have the torque due to the normal force plus the torque due to the weight of the pulley plus the torque due to the tension force is equal to I alpha. But what we see is that the normal force is acting through the axis of rotation, so we know that's going to be 0 because R is equal to 0, and that the weight is also acting at this location, and so the force of gravity basically has 0 torque in this scenario. So what we have is the torque due to tension. So write this out completely. The torque due to tension is equal to I times alpha. Now, torque we know is R times F times the sine of phi. And remember that phi is the angle between the R vector or the position vector and the force vector when placed tail to tail. So in this situation, we know that R is going to go across here like this. So this is going to be R for tension. And then we have our force of tension, and we know that the sine of phi is basically going to be 1 because phi is a 90-degree angle. So this is going to go to 1. So that's going to just give us R times F is equal to I. Now, this is a solid disk, so I is 1/2 the mass of the pulley, we got to be careful now, times the radius of the pulley squared times alpha. Now, in this problem, our objective was to determine the final velocity after the block falls through some distance d. So because we're doing that, and we know that the acceleration, the tangential acceleration of the pulley is going to be the same as the linear acceleration of our block, we need to go from angular acceleration to translational acceleration. And for that, we use our bridge equations. So we have alpha is equal to A over R. Remember, that comes from A is equal to alpha R. Okay, so we'll make that substitution, and we get R for the force is actually the radius of the pulley, so that becomes a capital R, times the tension force is equal to 1/2 the mass of the pulley times R squared, and then we put in A over capital R. And what we get, this R cancels with that one, this one cancels with that one, and now we're left with the tension force is equal to 1/2 the mass of the pulley times A. So now we have to figure out what A is. So how do we get A? Well, A is going to come from Newton's second law for the translation of the block. And that's just F net is equal to MA. And we've got two forces, one points up, the other points down, so it's going to become Ft minus Fg for the block is equal to a minus MA of the block. And the reason that this is minus is because the acceleration is in the down direction, and that makes it negative. Okay, so now all we have to do is make our substitution. This tension force here is the same as the tension force here, so we could put in 1/2 the mass of the pulley times A. And that's what we'll do. So we have 1/2 times the mass of the pulley times A minus mg, mass of the block times g, is equal to the mass of the block times A. So now we'll just rearrange it, and we end up with 1/2 mass of the pulley times A minus the mass of the block times A is equal to the mass of the block times G. Now you may have noticed I made a little mistake here. This is going to become positive because I moved this MB times A to the other side. That makes it positive. And so we'll factor out A, and we'll get 1/2 the mass of the pulley plus the mass of the block is equal to the mass of the block times G. And the acceleration, therefore, is equal to the mass of the block times g over 1/2 the mass of the pulley plus the mass of the block. All right, now we're not done yet because we're trying to find the final velocity. Since time is unknown, it's not been given, although we could find it if we wanted to. That could be another question related to this problem. We're not, but we could. What we need to use is an equation that does not include time. And for that, we would use the time-independent equation of motion. So using our time-independent equation of motion, we have v final squared is equal to v initial squared plus 2ad. And v initial is 0. So v final squared is equal to 2 times the mass of the block times g over 1/2 the mass of the pulley plus the mass of the block times d. And that is our final answer. Now, I like to, where possible and practical, to demonstrate for you all the fact that we can solve problems from any one of 4 perspectives as our starting point. And in this case, we're trying to find the final velocity, which you may have on your own said, hey, I think it would be easier to solve this using conservation of energy. And if that's what you thought, you might be right. Of course, everybody has their own, opinion as to which method is easier, but I say whichever one is easiest for you, the one that makes the most sense for you, is the one that you should use to solve the problem. So let's take a look at this problem now using conservation of energy. And for conservation of energy, we're just going to start with delta E is equal to 0, same as always. We have a rotating, this is a whole system now of interacting objects. So we have delta K of the block plus delta K rotational of the pulley plus delta UG for the block is equal to 0. Okay, now there are lots of other terms that we can include in this, but I'm hoping that by this point you should understand very clearly why the other ones do not exist. And I'm referring to elastic potential energy as an example. Why don't I include the kinetic energy of the Earth and the gravitational potential energy of the Earth? Things like that. You should know by now why those do not exist. So we have K final minus K initial plus K rotational final minus K rotational initial plus delta UG final minus delta UG initial. And remember that this here corresponds to the block. This corresponds to the pulley. And remember that the pulley has no change in gravitational potential energy because there's no change in height. So remember, there's a lot more terms I can add to this. I just gave you the most simplified form. Okay, and then finally, the delta UG corresponds to the block once again. Okay, so let's finish this out because you're going to be, I think, really surprised at how easy this was. Okay, so we have no initial kinetic energy in the block because it's going to start from rest. We have no initial kinetic energy of the pulley because it too will start from rest. And if we assume that y is equal to 0 whenever the block reaches its lowest position, then we could say that UG final is equal to 0. So we get 1/2 the mass of the block times v of the block squared plus 1/2 I omega squared is equal to, remember that all we have here is mgy, so that's going to be equal to the mass of the block times gy initial. Okay, so we've got to expand things out a little, and we have the 1/2 the mass of the block times v squared. We need the moment of inertia in terms of mass, so this is going to be 1/2 times, now the pulley is just a solid disk, so this is 1/2 mr squared And then omega, using our bridge equations, is going to be equal to v squared over r squared is equal to the mass of the block, g, y initial. Okay, so we can cancel some stuff. This r squared cancels with that r squared. None of the masses cancel, and so we just have some factoring in algebra to do in order to be done. And remember, this is the pulley. Forgot to label that. So we now have factor out v squared and multiply everything through by 2. So we get v squared times the mass of the block plus 1/2 the mass of the pulley. And when we multiplied everything through by 2, we lose that 1/2 and that 1/2, but we get a 2 out in front of that. So this becomes 2 times the mass of the block, g, times y initial. All right, almost done. We get v squared is equal to 2 mass of the block times g, y initial over the mass of the block plus 1/2 the mass of the pulley, and we're done. And if you compare this equation with the equation that we have up here, you'll see that they're the same thing. This y initial corresponds to this distance d, and so if you choose, you can rewrite that with a d instead of y initial. But that's it. Okay, so now you can see very clearly that you should be able to solve these problems using at least 2 different perspectives. They work together well all the time. All right. In this first perspective, our focus was on solving this using forces, which did require us to do some kinematics. And then down here, we decided to use conservation of energy because, quite frankly, that's a lot easier for a lot more people. It's not vector-based, and that's what makes it so popular, even among physicists, because you don't have to get caught up in the details of vectors. Now, keep in mind that if you were being tasked with determining acceleration, for example, that even though Newton's second law is just staring you in the face, I mean, it's just screaming at you, use me, because we have torques or rotational force, plus we have forces and all that, so we can use Newton's second law, which is vector-based. We can use Newton's second law to determine what the acceleration is. Remember, that's what we did here. But if you're really, really uncomfortable with Newton's second law, guess what? You can come down here. You can determine the velocity using energy. And then from energy, you can use your kinematics equations to come up with the acceleration.